Alright, so one last video, just for fun. Let's try to prove the odd order theorem for groups of order at most 1,000. So that means that if G has odd order, then G is solvable. Note that this is equivalent to saying that if it's odd order and not abelian, then it's not simple. Why? Because then it has a normal subgroup, and the normal subgroup and the quotient both have smaller order, so by induction, and they're both odd order, and so by induction they're both solvable as well. And so we're really going to go through and show that there are no non-abelian simple groups of order, odd order at most 1,000. So, or alternatively, there are no simple groups of odd order at most 1,000 except for the prime powers. Because if you're an abelian, a simple group and you're abelian, then you're a cyclic group of prime power order by the fundamental theorem of finite abelian groups. And so this is the claim we're actually going to prove using CELO theory. And so this is a common exam problem I had when I was a student, was just looking at all groups of order at most 100. And that was a time-consuming process. So you can imagine going all the way up to 1,000 would seem even worse. So we have to be clever. So obviously I'm not going to list the first 1,000 integers and cross them off one by one. Well, for one thing, I only have to list the first 500 odd integers. But one clever trick to note is that if you write your prime factorization, you can first ask whether or not the largest prime has exactly one CELO subgroup, whether or not that condition is forced. And remember, it has to divide the remainder part. So this forces a condition, which is that if this last prime is too big, namely if it's bigger than 31, then you're going to have a bit of a problem, because G is less than 1,000, and G is of the form 31 times M. You're going to end up seeing that M has to be less than 31, which forces NPK to be 1. Because remember, it has to be congruent to 1 mod pk, and it also has to divide the remainder term. So the point is, if your largest prime is large enough, larger than all the products of powers of all the other primes, then you already have a normal subgroup corresponding to the largest CELO, largest prime dividing the order of your group. And so we only need to worry we only need n where the largest prime factor is at most 31. So that rules out a lot of numbers already. In fact, that's what we're going to do. We're just going to look at the primes 31 on down, and we're just going to be looking at this condition that what you need is something congruent to 1 mod pk. So we're just looking at integers congruent to 1 mod pk. And not only that, we're going to be looking at ones that have to be odd, because we're looking at odd order. And finally, we want whatever we get to not have a prime divisor that's bigger than pk. So here is the list. I'm going to leave off the smallest 3 primes for last because that makes things a little easier later. 31 is congruent. Numbers that are congruent to 1 mod 31 is 32. Anything larger than that. So here on the right, I'm going to be listing m's with the property that m is congruent to 1 mod p. And with the property that p times m is less than 1,000. And so that's what we see on this list. These are possible orders that could pop up on groups, for which the largest prime might have more than one CeLO P subgroup. Note, these aren't the actual orders of the groups. You need to take these numbers and multiply it by this prime. And these won't actually be a complete list. You need to take these numbers and then multiply them by any common multiple that still gets you below this bound. So, I mean, this list alone isn't enough. You can also multiply by any other constant as long as you stay below 1,000. And that'll get you a complete list of all possible number orders where the largest prime could have more than one CeLO subgroup, P subgroup. And so here are the list of possible m values. Right now I'm not paying attention to the fact that m has to be odd yet. We'll rule that out in a moment. I just need things that are congruent to 1 mod p and satisfy this condition. And so we see we've gone from a list of 1,000 numbers to a much smaller list right off the bat. And to make life easier, I've already underlined cases where you end up with a prime divisor that's bigger than this prime. Because remember, this prime is supposed to be the largest prime in the factorization. So if you end up with a larger prime dividing m, then that contradicts the assumption on p. So for instance, 53 is prime, so we can rule that out. 23 is prime, that's bigger than 11. 34 is divisible by 17. 67 is prime. 89 is prime. And 78 is divisible by a prime that's bigger than 11. 2 times 39. Now we point out the other fact we need. We need these m values to be odd numbers because we want groups of odd order. So we've actually gotten all the way down to 4 numbers. These are 4 possible groups of odd order where the largest prime divisor might have more than one CeLO subgroup. And factoring them into primes completely, these are the prime factorizations. Multiplying them together, these are the actual orders. Remember, we can also scale by a constant, and if we get something less than 1,000, this gives another order for which the largest prime has a non-trivial CeLO subgroup. So technically, it looks like you should be able to multiply 350 by 1 by 2 and still get a valid group order of 702. But then again, that's actually even, so we don't count it. We need odd orders. Multiplying by any odd number gets you something larger than 1,000. Multiplying this by any odd number gets you something larger than 1,000. So these are it. Except I still have to consider groups of odd order involving only 3, 5, and 7. The smallest 3 odd primes. We'll consider that next. So right now, we're only looking at groups of odd order that are divisible by a prime that's at least 11. And we end up with only 4 examples. And now we remind ourselves that there was a homework exercise that if G is ordered product of 3 distinct primes, then G is not simple. So that rules off. those two. And something I'm going to use because we've already seen a proof of it, and it helps a lot in ruling out a lot of examples later, was Burnside's theorem, which takes care of products of powers of 2 primes. So the only interesting example with a large odd prime factor is 3 squared times 5 times 11, or 495. However, it turns out that this example falls down to a counting argument. So here are the possible number of CeLO 11 subgroups, the number of possible CeLO 5 subgroups, and the number of possible CeLO 3 subgroups. This means that there are about 450 elements of order 11, 44 elements of order 5. Those two together give you 494 plus the identity elements 495, and whoops, there's no room to fit in the elements of order 3. So there's too many elements. If you assume that there exists a group that doesn't have any normal CeLO subgroups. So if your group has order 495, it must have a normal CeLO subgroup, and therefore cannot be simple. Our proof is not done. Why? Because we still have to deal with the smallest 3 odd primes. The smallest 3 odd primes are 3, 5, and 7. Here are possible powers of products of 3, 5, and 7 that are smaller than 1,000. Plus, of course, you have to deal with products of just any 2 of them, 3 to the A, 5 to the B. These last cases I'm ignoring because they're all taken care of by Burnside's theorem. So we only need to focus on these 5 examples. So we've already seen for groups of odd order at most 1,000, we only really have, 8 serious examples once you include Burnside's theorem. And of course, this first one is a product of 3 primes. So we only have 4 more to go through. We'll start with the biggest order here, 3 cubed times 5 times 7. You're going to get used to seeing this list because it stays the same for most of these cases. The number of CeLO 3 subgroups is 1 and 7. The number of CeLO 5 subgroups is 1 and 21. The number of possible CeLO 7 subgroups is 1 and 15. This doesn't vary between all these remaining cases very much. One thing we immediately see using method 2 is that the smallest factorial that this has to divide, because of the 3 cubed, would have to be 9. So n cannot divide 8 factorial. Why is that? Because 3 cubed does not divide 8 factorial. And so that means we can't have anything of index less than 8 if you're going to be simple. So we realize that we run out of options. So that's our problem. Of course, if we need to remind ourselves what this means, if you suppose N3 is 7, then there's a homomorphism from G to S7 that comes from the action of G on the CeLO 3 subgroups. And if we're assuming G is simple, that means that the kernel is trivial. And therefore that the image of G is equal to G, and therefore that the order of G divides 7 factorial. As just pointed out, that can't happen. So that's a contradiction. Therefore this kernel is non-trivial, therefore there's a normal subgroup. Now we work on these 2 other cases real quick, as they're both proven similarly. I focus on these other large primes. In both cases, the idea is that if you assume that The number of CELO 5 subgroups is 21. 21 is not congruent to 1 mod 5 squared. So that means there exists a P and a Q in CELO sub 5 whose intersection is 5. If you let R be that intersection, then the point is this intersection is normal on P and Q. So P and Q are contained in this normalizer. P and Q are each individually non-trivial subgroups of 5 order 5 squared. So this normalizer has size strictly bigger than 5 squared, which means either it's the whole group, in which case you have a normal subgroup, or it's order 5 squared times 3, or 5 squared times 7. Either case, you end up with something of index less than 10. And because of the 5 squared, 10 is the smallest index that's actually allowed, because this order cannot divide 9 factorial. The same method, this was I think method 4 in the, or wait, no, this would be method 5 in the book, coupled with the method 4, I think, or no, method 3, the stuff where you actually talk about the normalizers. For this one, a similar approach is used, only with 7 squared instead. If you assume that you have 15 CELO 7 subgroups, because 15 is not congruent to 1 mod 7 squared, 2 of these CELO 7 subgroups have a non-trivial intersection. That non-trivial intersection is normal in P and Q. Let's call that intersection R. Therefore, its normalizer contains 2 groups of order 7 squared, so it has to be of order greater than 7 squared, which means it has to be of order 3 times 7 squared, 5 times 7 squared, or the whole group. So either this intersection is a normal subgroup, or you've got something of index strictly less than 14, either index 3 or 5. And why did I pick 14? Because of the 7 squared. You can't get something dividing 13 factorial. Finally, we're at this last order, 3 squared times 5 times 7. We'll assume n3 is equal to 7. If we let G act on the CELO 7 subgroup, or CELO 3 subgroups, we're going to get a homomorphism from G into S7. We're going to identify G with its image, and let's look at the normalizer in G. We'll let P be a CELO 7 subgroup. Let's look at the size of the normalizer in G of P. It has order 15. If we assume that there's 15 CELO 7 subgroups. Now let's look at the index in S7 of this normalizer. That's counting the number of CELO 7 subgroups in S7. That's why I'm picking 7, by the way. I'm not looking at 3 because then you're looking at groups of order 9 in S7, and that's a lot harder to calculate. 7 is easy because it's a cycle generated by a 7 cycle in S7, so that's just looking at 7 factorial. That's picking the elements in a cycle, but if you cyclically shift the elements in a cycle, you get the same cycle. And of course, there are always 7 cycles in any given subgroup, CELO 7 subgroup. So there are actually this many CELO 7 subgroups in S7, because this is counting the number of 7 cycles, and this is collecting them together by which group they belong to, CELO 7 subgroup they belong to. So that tells you that, oh, this shouldn't be G, this should be S7. Sorry about that. is 7 times 6, which does not contain a multiple of 5. So we see 15 does not divide this. So we end up with a contradiction. The normalizers don't divide each other, even though the normalizer of G is a subgroup of this normalizer. So we finally find our contradiction. Therefore, it can't be the case that these are both true and that G is simple. So G cannot be a simple group. So we ruled out the last possible order. In principle, one could pick a larger prime than 1,000. The textbook actually has a homework exercise where you go all the way up to 10,000. But that is a pretty big number, and it's the same principle, but a lot more cases. Although, again, the point of doing this demonstration is to show that the idea is that you wouldn't list all 10,000 integers and then do it the long way. You would do some sort of clever trick like what I did to reduce your list very quickly to just those cases where you know that the largest prime actually has an option. That gives you a much quicker way to list all the options, or all the cases you actually need to consider. Note, there were other shortcuts I could have taken that I didn't. For instance, one thing I should have also done was gone through my list and checked these conditions off the bat. In my case, for this small of an integer, that actually didn't help, but for something like 10,000, that could have been used to reduce the list of options further.